Hi guys, okay, so we're gonna do again your crash course on hearing, and again this is a very brief overview. You will do a much more meaningful and detailed series on the ear in semester 2. This is just to give you some idea of why you do what you do when you do the assessment for hearing that you're going to learn in clinical skills. Okay, so let's just do this quickly. Alright, so this is overall the basic structure and anatomy of the ear. If you look at the ear from the outside, this is what you're going to see. And this whole structure is what you call the auricle, and it has all these nice folds which are characteristic of its anatomy. And right here, just at the opening of the ear, there's this little portion of the ear, this cartilaginous portion that you call the tragus. And over here, this fleshy portion at the bottom, you either call the pinna or the lobule. And the big curved outer portion you call the helix. And this portion at that opening of your ear will actually go into this canal that you call the external auditory canal, and then that's going to meet up with your eardrum. And this whole portion here you can see is orange. This is your outer ear, and here you have your eardrum, which connects to three little bones, very small bones called the ossicles, and those ossicles are all connected to each other. And this whole portion here is what you call the middle ear, and that is also connected to this structure called the eustachian tube, which actually connects to your nasal cavity. And over here, the blue portion is your inner ear, and in the inner ear for hearing, what we're really interested in is this snail-like structure over here called the cochlea. And the cochlea is really important because it actually converts physical sound waves, which are vibrations of air molecules, into a neural signal, which will then be sent to the brain via the vestibulocochlear nerve. So if you look at this image, this is kind of showing you again a very simple image of how sound is conducted um, to the cochlea, where it is converted to a neural impulse, and from there will be sent to the brain. Okay, so imagine over here the auricle, sound waves, which are basically just compressions and rarefactions of air molecules, are going to enter the ear. Okay, and from the auricle has all those folds, and the folds of the auricle actually allow the sound waves to bounce in a certain direction and allows you to pinpoint the direction from which that sound actually entered your ear. So this sound wave enters and it goes through the external auditory canal and it reaches your tympanic membrane. Now what you want to recognize is also that these sound waves are waves, and like any wave, it has an amplitude and it has a frequency. The amplitude actually tells you how loud the sound is. The frequency tells you the pitch of the sound. So this tympanic membrane is going to move back and forth. It will move less with a low amplitude and more with a greater amplitude, and it will move at a speed that is equivalent to the frequency of the incoming sound. So it's translating that amplitude and frequency into specific vibration. And because that tympanic membrane is attached to your ossicles, and so ossicles have names, the three bones, the malleus, incus, and the stapes. So those bones will also vibrate, matching the amplitude and frequency of the tympanic membrane. And then that is going to transmit itself into the fluid of the cochlea. And what you can see here, there's this little foot piece of the stapes pressing on the oval window of the cochlea. And inside the cochlea, what you're going to see is this blue stuff represents a very special fluid. And in the middle of that fluid, you're going to see this structure called the organ of Corti. And as this fluid actually bounces back and forth following the vibration that is being transmitted by the stapes, that fluid is going to result in this organ of Corti also bouncing up and down. And as the organ of Corti bounces up and down at an amplitude and frequency matching the original sound wave, it will convert that bouncing into an electrical signal, and that will code the amplitude and frequency of the sound you're hearing and send that onto the brain. And once it reaches the brain, it will be processed and you will actually consciously perceive the sound that came in from the environment. So when you evaluate your patient, basically most of the time you're evaluating for hearing loss or reduced hearing ability. So the first step in this evaluation is to figure out whether you think your patient actually has a hearing loss or not. So the way that we do that in the clinic is actually the whisper test. So you want to test one ear at a time. So in order to mask one ear, you just want to rub one finger on the tragus, which we saw earlier. And if you try that on your ear, you will hear that there's kind of a staticky buzzing sound over one ear. So you're masking that ear from hearing. And then you stand and arm stand behind the patient. You whisper a series of letters and numbers, and you see if your patient can hear you correctly. If they can't, they may have some degree of hearing impairment, and then you need to figure out what kind of hearing impairment, because this makes a lot of difference. So is it a conductive hearing loss or a sensory neural hearing loss? If it is a conductive hearing loss, then it's either outer ear or middle ear, because that is literally conduction of the sound wave itself. It's not being converted to an electrical signal yet. So with the sensory neural hearing loss, it would involve either the cochlea or the vestibulocochlear nerve, or the parts of the brain itself that actually process the sound. Okay, so it's important to know that distinction. So how do you tell the difference? In the clinic, you do something called tuning fork tests. Of course, this again is not the world's most reliable. To really get a very accurate assessment of your patient's hearing loss, you need to do something called audiometry, which needs specialized equipment and specialized trained technicians. Okay. But in the clinic, you can do the Riney test, and all you need for this is a tuning fork. And you need either a 512 Hz or a 256 Hz tuning fork. In year 1, you guys use the 1 to 8 Hz tuning fork to assess vibration sense. You do not use that to assess hearing. Okay, so with the Riney test, what you do is you take your 512 Hz tuning fork, you activate it, and you're actually going to press it behind your ear, and you feel behind your ear, you're going to feel a bump right there, and that is your mastoid process. So you have to press your tuning fork against your mastoid process, and you're going to, not yours or your patient's, and you're going to wait until the patient says you can no longer hear the buzzing sound. You're going to shift it to the front of the ear like this. And in an ear that is actually working normally, you will be able to hear it at the front of the ear even when you stop hearing it at the back of the ear. And this works because of the difference between bone conduction and air conduction. Under normal circumstances, your ear is meant to hear better through air conduction. This air conduction is what you normally hear when sound waves enter through the external auditory canal, make your tympanic membrane bounce, and then go and trigger your cochlea to bounce and translate that sound into an electrical impulse which goes to your brain. So that is the way you're supposed to hear, and that is the optimal way by which sound reaches the cochlea. Bone conduction, on the other hand, if you think about it, your cochlea is actually embedded within the bone of your skull, and your mastoid process is part of your skull bone. So if you press that tuning fork on your mastoid process, you actually physically create a vibration in the skull, and that vibration can be transmitted directly to the cochlea through the bone and make it vibrate, and therefore create an electrical impulse which then goes to your brain. But as you can imagine, you would hear better through air conduction than bone conduction, provided your ear is working normally. Weber's test is a little bit different. You just take that tuning fork and you press it somewhere to the midline. Normally, we press it here over the glabella, okay, or you can press it over the vertex of the skull. Some people also press it over the chin, and some very hard to hear cases, you can actually press it over your incisors, but people really rarely do that. Okay, and normally what you're supposed to get in Weber's test is, you can imagine pressing in the midline, and this sound is vibrating through the skull bones to reach your cochlea. So you would expect to hear it normally on both sides if your ears are normal, and in most cases this is what happens, but in about 30% of the population, even those with normal hearing, it actually sounds louder in one ear than the other, so it's not the world's most reliable test. But it's all you got, so it's what you need to do in the clinic. Okay, and if you actually do Riney and Weber's tests, you will then actually be able to interpret, based on your findings, whether this is more likely a sensory neural or a conductive hearing loss. And you guys will discuss this more in the class with your tutor, and you'll do this in a lot more detail when we get to SAM 2. Okay, so that's all the fairly straightforward stuff you do on the outside, but there is a special tool that you use to actually look inside the ear, and that is called an otoscope. And the handle is actually the same as the ophthalmoscope that you use to look at the eye, but you change the headpiece so that you can actually look into the ear. And this is how you use it. You actually look into the ear using this special earpiece and the otoscope head. It actually shines light into your ear canal and allows you to visualize your tympanic membrane. So this is what you should see in a normal ear, a nice, healthy, pearly tympanic membrane with a cone of light. And if you look behind it, you can actually just sort of make out your ossicles. Okay, a lot of things can look different in anybody's ear, and for most of you guys, if you look into your friend's ears in class, you're probably going to see a lot of earwax, so that is also normal. Okay, but this is basically what you guys are going to do in the class. Your tutors will tell you more about it, but hopefully this gives you some idea of what you're going to do and why. Okay, so good luck, have fun in class. Bye guys.